So, what we are currently investigating is how to realize a higher order filter with the strategies which should be familiar to you, such as the Butterworth or Chebyshev filters strategies. So in this presentation, sorry, I have some problems with the setup. In this presentation, I will try to show you the basic strategies, if I can. Totally stuck. Okay. So Butterworth filters are characterized by transfer function like this one, like the one depicted in this formula. The idea is that there are two main parameters in the definition of this analytical formula. That is the order of the filter, which is capital N, and this parameter epsilon, which is somehow related to the characteristic of the transfer function. More specifically, if you look at this function, you can see that is a monotone descending function, and basically the limit of the passband region, omega sub p, is defined also the specific value of the amplitude of the transfer function, which depends in turn on the parameter epsilon. Okay, so basically, if we get back to the definition of the parameters A max and A min in the filter specification, we know that A max is the maximum ripple that we have in the passband region, and therefore this limit is set in this family of filters by parameter epsilon. Okay, so you see epsilon conferred in the definition of this point here. The closer epsilon is to 0, the closer is this drop here to 0, which means a very small ripple in the passband region. Okay, so you control epsilon to set this limit. And then the order of the filter somehow is related also to the selectivity of the filter. Okay, so basically the idea, let me try to see if this is working as well. The idea is that you start from the specification that you have concerning A max to define the value of this parameter epsilon. Okay, so basically, if you flip this formula to highlight epsilon with respect to A max, you get this this information. Okay, so first step in the design strategy, set the value of epsilon with this formula. In the second step, you have to analyze the possible selectivity of the filter. So you have to select the order, capital N. How to do that? Well, if you remember, the specification you have are related to omega sub p which is the limit of the passband region, omega sub s, which is the limit of the stopband region, and the parameter A max that we have already used, and A min, which is the minimum attenuation that you have in the stopband region. Okay, so the attenuation in the stopband region is depicted in this formula here. So you see that basically the order of the filter sets the attenuation in the stopband region. What you can try to do is to, if you have a monotone descending function, is to look at the very limit of the stopband region, because this is the highest possible value that you have in this region. So you compute the attenuation in this region by exploiting the formula that we have seen in the previous slide. And here it is clearly highlighted the dependency on the order of the filter. So the idea is that this exponent n should be an integer. Okay, so you iteratively change n, starting from 2, 3, 4, etc., until you get an attenuation which is higher than A min. Okay? Once you have found an attenuation higher than A min, you set the order of the filter at that specific value. Okay? In this formula, all the parameters are predefined. Omega sub s is a parameter given by the specification. Omega sub p is given also by the specification. Parameter epsilon is taken from the previous calculation. The only parameter which is unknown is the order of the filter n. And you select n as the first one which determines an attenuation larger than the specification. Okay? So in this way, you have set the two parameters which are needed to design a Butterworth filter, capital N and epsilon. Okay. Once you have this information, you have to find the pole position, which are univocally determined by the value of N and epsilon. So I don't know if you can read the light blue characters, but basically there is a geometrical construction of the pole around the complex plane. So first of all, let me try to change the setup, because this one is very difficult to handle. Just 1 second. I'm sorry, guys. We completely stuck. Okay. Okay, so this is the calculation of epsilon, and this is the calculation of the order of the filter. Then we have to place the pole depending on the order of the filter and epsilon around the complex plane. So in particular, in the Butterworth family implementation, the poles are arranged on a circle, okay? And the radius of the circle is given by this value, that is omega sub p, the limit of the passband region, which is given by the specification, 1 over epsilon, the parameter that we have found in the first step, to 1 over n, which is the order of the field. Okay? This is the distance between the pole and the origin, while the angular spacing is given by this formula. So the first pole is distant pi divided by 2n as from the vertical axis, and then the separation for all the remaining poles is pi divided by n. So for example, suppose that the order n is equal to 2, then the distance from the poles to the origin is omega sub p time 1 over epsilon to 1/2, and the distance between pole 1 and the angular distance between pole 1 and the vertical axis is equal to pi divided by 4, that is pi divided by 2n, so n is 2, so pi divided by 4, and the distance between pole 1 and pole 2 is pi divided by 2, that is 90 degrees. Okay, so you have an algorithm to construct the pole positions once you know the order of the filter n and the parameter epsilon. Okay, it is a pure mathematical procedure. So once you have this information, you can extend it to higher order filters. So this is the case for the order equal to 3. When the filter is order filter is equal to 4, you will have this range. So in the Butterworth family, the poles are arranged in this way. You can have either odd or even order filters. If the order is odd, then you have one real pole, and all the remaining are conjugate pairs. Okay. Otherwise, you have just conjugate pairs. Okay. This is an example of the construction of Butterworth filter for a cutoff frequency for equal to 1 radian over second. Okay, so again, there are 3 basic steps. So find epsilon, find the order, and finally use the geometrical construction to determine the pole positions. Okay, this is the strategy to design Butterworth filters. Butterworth filters are characterized by a step response with some ripple. Okay, so if you apply a step function to the input of a Butterworth filter, what you get is this kind of trend, which it is more or less pronounced depending on the quality factor. Okay. Similarly, the group delay, which represents the delay from which each frequency component experiences from the input to the output, is not flat. Okay, in the whole frequency range. There are some frequencies which are affected by higher delays. Okay, this means that the Butterworth filter induces some kind of distortion in the signal at the end. Okay, so it is not a perfectly, let's say, linear effect. Okay, then we can jump to the Chebyshev filter case. Chebyshev filters are characterized by frequency response like this one. So you see that there is a sort of oscillation in the passband region, but you can control the entity of this ripple again by resorting to parameter epsilon. Okay. So the expression for transfer function before and after the stop band region are provided in this slide. So the idea is that in the Chebyshev case, you cannot express all the frequency response with just one formula. You have 2 separated formulas. After omega sub p, you have a monotone descending trend. Okay, so first step is related to the analysis of the maximum oscillation in the passband region, which is related to parameter epsilon. Okay, so pretty much like we have seen for the Butterworth case, the first step in the Chebyshev filter design is given by the setting of this parameter epsilon. Once you do that, you can compute the second parameter, which is the order of the filter, n. Again, you apply a similar procedure with respect to what we have seen before. The unique difference is given by the fact that the formula has changed, of course. So you iteratively change n, taking into account that all the other parameters of the formula are known, until the value, this value here, a of omega sub s, the attenuation at this point, is higher than the specification provided by the program. So just let me recall that you have as designer 4 specifications. A max, the ripple in the passband region, A min, the minimum attenuation that you have in the stop band region, omega sub s and omega sub b. So the angular frequency limit of the passband region and the angular frequency limit of the stop band region. So you enter all these parameters in this formula. Well, A max is hidden in parameter epsilon, and you iteratively change n. So let's say that you want an attenuation which is more than 40 dB. Okay, you change n until this value here is larger than 40 dB. Okay. So this is the second step in the design procedure. The third step, as before, is related to the positioning, the pole positioning in the complex plane, okay, basing on the value of n and epsilon. The formula here is slightly more complicated because the poles in the Chebyshev case are arranged in this ellipsoid, not on the circumference. Okay, so the distance from the poles to the origin changes depending on the pole pair. Still, they are paired with complex conjugate poles or just single real poles when the order of the filter is odd. Okay. Please take into account the fact that in this formula, this is not 1 over the hyperbolic cosine, but this is the inverse function of the hyperbolic cosine function. Okay, so is r cosine hyperbolic function. Okay, so this symbol -1 means the inverse form. Okay, same here, of course. Okay, you should, I guess, find this formula already in multiple scripts. I don't know if you are familiar with the usage of MATLAB or similar tools, but probably, I mean, my suggestion is to try to implement these formulas in the software so you can compute them automatically. Okay. So, quick poll. Have you ever seen this kind of design procedures? Never. No, not even in statistical signal processing courses or something like that. No. Yeah. Because basically, this formula are also used for digital filters. Okay, so. These are very old tools which can be traced back to the era of mechanical filters, okay, with dampers and masses, okay. So again, this is a sort of recap of the design procedure. And what is shown in this picture is the fact that the group delay induced by the Chebyshev filter is even more with respect to the Butterworth filter. So Chebyshev filter tend to generate a distortion in the signals, especially around the cutoff frequency. Okay. This is due to the fact that for a non-distortion action, we should have a flat group delay response, but you see that there are huge oscillation in this case. So this is a summary of the Chebyshev filter design procedure. We went through all these passages, and this is sort of mirroring of what we have seen in the Butterworth case. So basically, in the filter design procedure that will be assigned to you, it will be specified whether you have to design a Butterworth or a Chebyshev filter. Okay? And then you will pick up the strategy to select, to define the pole position. Once you have the pole position, you can group them in complex conjugate pairs and find the second order transfer function which correspond to each complex conjugate pair. Okay? Once you find this transfer function corresponding to the chain of second order transfer function, you select one of the possible strategy to implement the second order transfer function with circuit topologies. So you can pick up the Simon T topology, the Thomas topology, LCR, whatever topology you prefer. Okay? This is a comparison of filter responses related to the same order, n equal to 5, and the same cutoff frequency. For the Chebyshev, Butterworth, and Bessel case. Bessel is another family that we will not review in this course, but it's also very commonly adopted. What can be clearly seen is that the Chebyshev is the most selective one. Okay, so if we use order filters of the same order, then you can get higher attenuations with the Chebyshev filter, okay, with respect to the other. However, the Chebyshev behavior is slightly worse as far as the step response is concerned, because since the distortion is larger, when you feed your filter, for example, with a square wave, what you get are this huge ripple effect in the time domain. Okay, so this is a time waveform. So please do not make confusion between ripples in the time domain and ripple in the frequency response. Okay. Ripple in the frequency response are controlled by parameter A max. The ripple in the time domain are somehow related to the frequency response, but mostly they can be associated to the irregularity of the group delay response. Okay, the group delay, by the way, is given by the derivative of the phase with respect to the angular frequency. Okay. Okay. Now, let's jump to the whiteboard if my PC will collaborate to see some example of filter design and more specifically to the definition of the whole topology for higher order filters. So once again, I will provide you the specification of Amax, Amin. You will find the pole positions, and then you have to design the actual circuit. So we are going to review some example of this. Okay. Okay, so suppose that we have to design a Chebyshev filter and the order is the seventh. You are provided with the value of A max, A min, omega p, and omega s. From this quantity, you find all the pole positions, P1 to P7. You group this pole in complex conjugate pairs. So you will have, say, P1, P7, which are complex conjugate, P2, P6, which are also complex conjugate, and P3, P5, and finally you will have P4, okay? So you find then the transfer function which correspond to each of this pole. These are second order transfer functions, okay? So for second order transfer function, you can define omega null and q, okay, from the expression of the transfer function. And this is all you need, okay? So omega null and q for the first complex conjugate pair, for the second, for the third one, and finally for the fourth. Well, actually, the fourth is a single pole, so you just have the information related to omega null, okay? The pole position, okay, the angular quickness. So, suppose that you went through all this calculation, and this is the result. These are the results you got. So, for the three stages, three second order stages, and for the first order stage. So F null, which is basically omega null divided by 2 pi, is 7.8 kilohertz for the first second order stage, 6.5 for the second, 4.5 for the third one, and finally it is 3.1 for the first order stage. The quality factor Q, after all this calculation, is 5.56 for the first case, 1.66 for the second, and 0.79 for the third. Okay, now you have to implement this with a circuit topology, okay? You have to implement all these stages, 1, 2, 3, and 4. One way to do so is to use the Salonen key topology. Salonen key topology is something like this. So resistor, second resistor, capacitor connected to the ground. Then you have a buffer with realized with a non-inverting configuration. And a feedback loop in which you have another capacitance. When the silent key is implemented with the so-called lazy strategy, omega null is given by 1 over RC. The two resistors are equal and the two capacitors are equal in this strategy. And the factor Q is controlled by this expression. 1 over Q is 3 minus K. Let's give a name also to these two resistors. So this will be resistor A and this is resistor B. And the gain of the silent key topology is given by the conventional expression for the non-inverting topology. That is 1 plus RB divided by RA. So we have to set omega null and 1 over Q according to these values. And therefore, we have to translate these expressions into parameter value, circuit parameters value. So let's pick up this table. And use it for all the computation. So for each stage, we have to design the specific gain K of the non-inverting configuration. Then the circuit parameters, RB, which is this resistance here, RA, which can be set arbitrarily because basically we have 2 degrees of freedom to set the value of K. Then we have to set the value of the resistance R and the value of the capacitance C. This should be done for all the second order stage. Okay, so if we apply this formula, so we flip Q and then we compute K from this formula, we find that in the first case, K should be 2.82. The second case, this should be 2.4. And in the third one, it should be 1.79, more or less. Okay? Suppose that in your storage, you have a batch of resistor whose value is equal to 10 kilo. Okay, so you wanted to use as much as possible this set of resistors. Okay, so we will set RA to be equal to 10 kilo for all the configuration. $10 kilo, 10 kilo, 10 kilo. Okay, so you have computed the parameter K, so now you can compute RB, provided that RA is given by this formula. So for the first case, RB should be 18.2 kilo. For the second case, this should be 14 kilo. And for the third one, it should be 7.9 kilo. Okay, once you have set RB and RA, you are controlling K, and therefore you are controlling Q. Okay? The only thing that must be set is now the value, the proper value of RC to get the desired angular frequency. Okay? So we use this formula to achieve this goal. Basically, you have 2 degrees of freedom. You can change both R and C, or to simplify your task, you can set the capacitance to one specific value, say 1 nanofarad, a very common one, and select R so that this equation is fulfilled. If you do so, R should be 20.5 kilo ohm for the first combination, 24.3 kilo ohm for the second one, and 35.7 for the latest one. Okay, please check if these calculations are correct. Factor Q for the first order stage is not computed. Okay. In the last implementation, the one related to the first order filter, what you need is to use this topology. So R1 connected to the negative input of an op-amp, and then R2 and the capacitance. This is one of the first topologies that we have seen in this batch, in this chapter, let's say, related to filters. So this is how you implement a first-order active filter. In particular, this filter angular frequency is controlled by the product of the capacitance C with the resistor R2, while the DC gain of this configuration is equal to minus R2 over R1. Okay? So in the lazy strategy, the gain is somehow imposed by the quality factor. Okay, so the gain of each stage is given by this formula. Okay, suppose that you wanted to implement a filter with a definite DC gain. So the global DC gain of the seventh order Chebyshev filter should be equal to, say, 10 volts over volts. Then, due to the strategy that you have implemented, you have imposed so far these gains. Okay, so you can use the first order stage to balance the gain that you have applied so far. So if you multiply the gain of the first stage times the gain of the second stage times the gain of the third stage, what you get is this quantity times this one should be around 11.66 volt over volt. Okay? While the total DC gain you want is equal to 10. So the gain So this is first, second, and third. So K1, K2, and K3. So the gain of the fourth stage multiplying the gain accumulated in the previous stages should be equal to 10. So basically, the gain of the fourth stage will be 10 over 11.66. This should be equal to R2 over R1. Okay, so we have to use this expression and this one to set the value of C, R2, and R1. We have three circuit parameters to set basically two specifications. Okay, so we have some degrees of freedom to achieve the result. One way to do so is to set the capacitance value to, say, 2.2 nanofarad. This is an arbitrary choice. Okay, if you select this quantity here, then you must pick up as resistor R2 this value here, 21.5 kilo, because C times R2 with sufficiently good approximation gives you the inverse of this quantity. Taking into account, it's very important to consider angular frequencies. Okay, so you must transform this frequency into an angular one. Okay, so you multiply this quantity times 2 pi to set the value of the product C times R2. This is very important. Okay, so do not forget the conversion between angular frequencies and frequencies. Okay, 1 over the time constant, the product CR is related always to angular frequencies, not to frequencies. Okay, so you have set R2, then you plug R2 here, and finally you define the value of R1, which imposes this relationship between R1 and R2. So in this specific case, you need an R1 which is equal to 24.9 kilo. Okay, so let's make a short break, and then we will design the whole topology. So basically, we have specified all the circuit parameters which are needed for the final design.
You weren't thinking about this in the Java before, so.
Okay, so we can use this table now to design the whole circuit. Okay, so we have to plug 3 silent and key stages and then the first order one. So the whole circuit will be something like this. First the silent and key, then the second one, third one, and finally the first order stage. For this first stage, we have that the resistor R are 20.5 kilo ohm. The capacitance is 1 nanofarad, both here and here. RA is always 10 kilo ohm for all the silent and keys configuration, while RB is 18.2 kilo ohm for the first one, 14 kilo ohm for the second, and 7.9 kilo ohm for the last one. R is 24.3 kilo ohm here and here, of course, because we are implementing the lazy strategy. So lazy strategy means in each stage, same resistors and same capacitances. Well, speaking of which, 1 nanofarad, 1 nanofarad, 1 nanofarad, and 1 nanofarad for all the stages. Then we have these two resistors which are equal to 35.7 kilo ohm. And this concludes the implementation of the second order transfer function. Then we have to take these values for the first order stage. So first order stage is characterized by 2.2 nanofarad capacitance, 24.9 kilo ohm for resistor R1, and 21.5 for resistor R2. Okay, so this is the implementation of the global transfer function. The lazy strategy has, however, some limitations when we consider the sensitivity to parameter variations. Okay, so one possible alternative is to switch to the strategy for the Sun and key implementation that we have called SMART. Okay, so we are going to implement the same exact topology, but with different parameter selection in order to minimize the sensitivity to parameter variations. The SMART strategy is based on the assumption that K is taken equal to 1 for all the stages. Okay, and the resistor R is also constant. So what we are going to change is just the ratio between C2 and C4. Yesterday we found that when implementing the SMART strategy, this relation is valid for the assessment of omega null. That is, omega null is 1 over R times the square root of C2 times C4. And then the second parameter of the second order transfer function, that is the quality factor, is set by taking into account that 4 times Q to 2 is equal to C2 over C4. So we can rewrite the previous table by taking into account this new relationship. So let me copy and paste so the topology will not be based on non-inverting configuration, the buffer that we have used before, but we are going to use unitary gain buffer because the gain K is equal to 1 mandatory. So basically, we can cancel this column and also this one. But we need to specify C2 and C4. So here we will have C2 and here C4. The values shall be different So we can cancel the old one. Okay, so K is going to be always 1. So we can start from this expression. So if we plug the value of Q in this expression, we have the desired ratio for C2 over C4. So for example, for Q equal to 5.56, then the C2 over C4 ratio must be equal to approximately 123.9. Okay, so there is quite a huge difference between C2 and C4, but still this ratio is possible. Okay. So basically, we can select, for example, a C4 which is equal to 82 picofarads, and to comply with this requirement, C2 should be around 10 nanofarads. C2 for in the second case, Q is 1.66. So luckily, the ratio between C2 and C4 can be much smaller, and you have several possibilities to realize the desired value. One possible mean is to set C2 equal to 2 nanofarad and C4 equal to 200 picofarad. Then for Q equal to 0.79, a possible way to implement the desired value is by setting C2 equal to 750 pico and C4 equal to 300 pico. Okay? Once you have set this ratio, you can then pick up the desired value of R in order to be compliant with the specification on the angular frequency, omega null. So in the first case, you need a resistor which is 20.5 kilo. Second case, you get a sufficiently good approximation if R is 36.5 kilo. And in the third and last case, it is okay if you set R equal to 75 kilo. The global DC gain of the circuit, once again, should be equal to 10. So if the gain of all the second order stages are set to 1, then the only way to achieve the desired gain is to exploit the first order stage. So you set the gain of the first order stage to be equal to 10. So again, for the first order stage, C times R to 2 is equal to 1 over omega null, and the gain minus R2 over R1 should be indeed equal to minus 10. Okay, to achieve the desired DC gain. This is, let's say, the amplitude, okay, the modulus of the DC gain. Okay, so if you pick up a capacitance whose value is 680 picofarad, then R2 should be equal to 73.2 kilo, and R1 should be equal to 7.32 kilo. Okay, to get the desired DC gain. Okay. So the new Salon and Key implementation, based on the smart strategy, is slightly different in the sense that we have no more the inverting the configurations, the non-inverting the configurations. So still we have two resistors which are equally sized. Then you have the feedback loop to realize the unitary gain buffer, and finally C2 and C4. This is the input, and this is the output of a single stage. So you have to use 3 stages. So again, resistors, C2 and C4, and unitary gain buffer. Last, Salon and Key. And finally, the first order stage. This is very important because it allows you to realize the desired DC gain. Okay, so you can then use all the information derived from this table. So 20.5 kilo here, 20.5 kilo here. Here we have 36.5, 36.5 kilo, and finally 75 kilo here, 75 kilo here. Then this is 7.32 kilo and 73.2 kilo. In the first case, we have a capacitance which is 82 picofarad here and 10 nano here. Then we have 300. No, 200 pico. And 2 nano. And finally 300 and 750. The last one is the capacitance C680 picofarad for the first test. And this is the implementation which can be achieved by using a 7-key topology with the smart strategy. Okay. Let's finally see the alternative based on the Thomas circuit. So the Thomas circuit is provided by this configuration here. So as you may remember, it is more complex because you need 3 op-amps to implement each second order stage. The first stage in the Thomas circuit is a complex combination of integrating circuit, inverting circuits, and also a circuit which is mixing the input with feedback loops. While it is much simpler, the elements which are used to realize the second integration step. And finally, we need an inverting topology at the very end. It is important to pick up the output for the next stage here and not here if you want to keep the same phase alignment. Okay. Here you have -1 multiplication, while you may be interested in having same phase for input and so this is the low-pass output. This is, let's say, C1 and C2. This is resistor R2. This is R1. This is R3, R6, R4, and R5. The transfer function related to this topology, VLP over VI, is given by this formula, R6 times R4 divided by R1 times R5, S22, which multiplies C1, C2, R3, R6, R4 over R5, plus S multiplying C2 times R3, R6, R4, R2 times R5, plus 1. It is useful to derive the conventional second order transfer function parameters, in particular omega null. Well, you can clearly see that there are no zeros in this configuration. That's the reason why this is a low-pass function. So omega null is given by this formula, 1 over the square root of the C1 times C2 times R5, R6, times R4 over R5. And Q parameter is given by this formula. So C1 times R2 to 2 divided by C2 times R3 times R6 times R5 over R4. Okay, these formula are provided in the study materials, in the study material, or in every textbook related to filter design. As you may see, we have plenty of degrees of freedom, so there is no need to set each value individually. We can group them. So, for example, you can take R1 equal to R3 equal to R6 equal to a generic value R. Then you can keep R4 equal to R5 and C1 equal to C2 equal to a predefined value C. When this is true, then R2 must be equal to Q times R, and omega null is given by 1 over CR. Okay, so basically we have to set just three values for this topology: C, R, and R2. Okay, again, you can build another table, this time related to the tau-Thomas implementation, by associating the value of Q and omega null to CR and R2. You have three circuit parameters, two specification, so you have some degrees of freedom. Okay, 1 degree of freedom actually to define the final value. So let me give you directly the whole circuit topology, okay, with the actual parameter which I've calculated. So DI is entering the first tau-Thomas circuit. We need 3 tau-Thomas circuits to implement each second order transfer function, and then the first order circuit. So first tau-Thomas. Then we have the integrator. Then we have the inverting circuit. This op-amp here has multiple feedbacks. Okay, and the output is taken from here. And this is provided as input for the second stage. Again, multiple feedbacks. The second integrator. And the inverting circuit. And this is the feedback loop with an additional resistor here. Okay. One more tau-Thomas. Too fast? It's okay? Okay. So let's start to plug some of the circuit parameters. So in the first stage, this resistor here is 16.9 kilo. This is 16.9 kilo. This is 35.3 kilo. This is 12 nanofarad. No, sorry, this is 95.3. And this is 16.9 kilo. And this is 1.2 nanofarad. Well, actually, also this one is 1.2 nanofarad. This is 10 kilo, and this is 10 kilo. Okay? Again, these values are computed by starting from the specification related to Q and omega naught. So this is the first stage. Second stage, 16.2 kilo, which is equal to this value here, 16.2 kilo, which is also equal to this guy, 16.2 kilo. Okay? All these three terms are always equal to each other. The gain here should be always 1. So if you have a bunch of 10 kilo resistor, you can use that. The only thing that you need is that this guy is equal to this one. So 10 kilo, 10 kilo. Okay, then the capacitance, it is 1.5 nanofarad for this and 1.5 nanofarad for this one. And this resistor here is Q times R, and in this specific case, this is equal to 26.7 kilo ohm. Okay, that was the second stage. Third stage and last. So Thomas. So this resistor here is 16.2 kilo, 16.2 kilo for this guy, and 16.2 kilo for this one. 12.7 kilo for this guy. In the last stage, the Q factor is smaller than 1. That's the reason why this guy is less than this one. The capacitance is 2.2 nanofarad for this guy and this one. And 10 kilo and 10 kilo are needed for the inverting configuration. Okay? Last step. It's the first stage topology. Could you fit this circuit on your block notes? So 4.2, well, actually 22 kilo here and 42.2 kilo here, and finally 1.2 nano here. And this is it. Okay, this is the output finally. Well, this is useful to see how complex can be the tau-Thomas if you have multiple stages. So this is all one filter, okay, made of 10 opa, okay. So all these three topologies that we have seen, silent key lazy, silent key smart, and tau-Thomas are realizing the same functionality. However, there is a distinction for what concerns the capability to address the sensitivity to variation. So if you run a Monte Carlo simulation by randomly changing the nominal value of resistors and capacitors, taking into account even small variations, just 1% for resistor and 5% for capacitors, this is what you get with the first design strategy. Okay, this is the practical simulation of the circuit that we have sketched on the whiteboard. So you see the silent and key strategy, which we are referring to as lazy, generates a huge variation in the actual behavior of the frequency response. While if we apply the smart strategy, still you can see some variation, but it is confined in a narrower band. Okay, so it's much more tolerant. Also, the tau-Thomas behavior is quite good. Okay, so tau-Thomas slight changes, but most of the changes are just related to the gain, which is typically a parameter which is not set that much precisely. Okay, even if the gain changes a bit, it's not a big problem typically. Okay. Okay, this is it for today. Next time will be next Monday, because actually Friday, I don't know why there is there are no classes. I have already, let's say, shown to you most of the strategy which is needed to implement your design. On Virtuale, you can find the individual specification for the filter. Okay, I've just dropped the specification. So next time, if you want, you can bring with you your PC and start the design. I think that in 1 hour or 1 hour and a half, we will complete the discussion, and we can use the remaining time for you to start the design of your film. Okay, if you need clarification, if you have troubles in finding the circuit parameter, please ask. Thank you very much for your attention, and see you next week. Arrivederci. Arrivederci. Arrivederci.